Welcome to Module 5 of the NFPA20 training course, which focuses on the installation requirements for fire pumps. This module is critical because the proper installation of a fire pump is just as important as its design and component selection. An incorrectly installed pump can fail during a fire emergency, rendering the entire protection system ineffective. In this module, we will cover a wide range of topics, from the fundamental construction and separation requirements for the fire pump room to the specific details of piping, valves, the pump, the critical components. We will delve into the reasons behind these requirements, explaining the fire safety and engineering principles that ensure the pump will operate reliably when called upon. Understanding these installation criteria is essential for engineers, designers, installers, and authority having jurisdictions to verify that a fire pump installation is code compliant and, most importantly, ready to perform its life-saving function. We will address a fundamental safety requirement, protecting the fire pump from a fire elsewhere in the building. Section 414.1.1 and its accompanying table 414.1.1.2 provide the specific fire separation requirements for an indoor fire pump. The core principle is that the pump room must be constructed to withstand exposure to a fire for a specified duration. The required separation depends on the sprinkler protection of both the pump room and the surrounding building. As the table shows, if the exposing building is not sprinklered, the pump room requires a more robust 2-hour fire-rated separation or a 50 feet distance. However, if the entire building, including the exposing structures, is fully sprinklered, as per NFPA 13 or 13R, the required separation is reduced to a 1-hour fire rating of or the same 50 feet distance. This recognizes the enhanced safety provided by a complete sprinkler system. Then we ask a question. Chat question to our students: what sprinkler protection design is required for the fire pump rooms? The answer is crucial. While NFPA 20 allows for reduced separation when the building is sprinklered, the pump room itself is one of the few areas where sprinklers are often required, even if the pump serves a non-sprinklered system. This is because a fire in the pump room could disable the entire water-based fire protection system. The design must follow NFPA 13, and special consideration is often given to the pump and controller to minimize water damage to this critical equipment. Next, we are transitioning to the outdoor fire pump requirements. In section 414.1.2, 414.1, for outdoor pump houses, the focus shifts to protection from weather, physical damage and freezing, while still considering exposure to fires from nearby buildings or structures. A fire pump room is more than just a space to house equipment. It is a dedicated environment designed for reliability. Sections 414.2, 414.7 to 414.7 in between outline the general requirements for this space. We have already discussed the construction and fire separation. Other critical factors include the adequate access for maintenance and operation, which includes clearances around the equipment. The room must be provided with sufficient heating to prevent freezing, as a frozen pump is useless. Proper permanent lighting is required for visibility during an emergency or maintenance. Ventilation is also essential, especially for diesel-driven pumps, to remove engine exhaust and prevent the buildup of heat that could affect performance. Finally, the drainage must be provided to handle the water discharge from the pump casing drains, relief valves, or testing, preventing flooding that could damage the pump or controller. Then also we have specifics for diesel and electric pumps that we can see in later sections. Next, we can introduce the concept of the power transfer assembly, which is defined in 3.3.27. This is the mechanical connection, the coupling and shaft that transfers energy from the driver, whether an electric motor or a diesel engine, to the pump itself. Its reliability is paramount. Sections 6.5 and 11.2.3 provide the specific requirements for this assembly. The coupling must be designed to handle the full horsepower and the torque of the driver at the pump's maximum expected load. It must be aligned with extreme precision to prevent excessive vibration, bearing wear, and potential shaft failure. Proper alignment is not a one-time task during installation. It must be verified periodically as part of a maintenance routine. A failure in this power transfer point will stop the pump as effectively as a failure of the driver or the pump itself, making this coupling issue is very critical through sometimes though overlooked component. Then we pass into the subject of the circulating relief valves, as covered in 4.13. If the pump cannot discharge water, the water trapped in the casing and piping heats up quickly. We call this is a churn. So a circulating relief valve protects the pump and engine by sending overheated water back to the suction source or drain. The circulating relief valve is a small pilot-operated valve that bypasses a controlled amount of water from the pump's discharge back to the suction or drain side, ensuring a minimum flow through even when the fire pump is not actively supplying water to the sprinkler system. Then we have another question. Let's have a question. The first question we ask is, what pumps do not require a circulating relief valve? The correct answer is B, diesel-driven pipe pumps with cooling water bypass lines. A cooling water bypass line ensures water continues circulating even if the discharge is closed and the pump is at churn. This continuous flow removes heat and prevents overheating. Because cooling is already guaranteed by the bypass system, an additional circulating relief valve is not required. The second question, how are fire pump and suction supplies sized? The correct answer is C, NFPA20 size tables. While NFPA20 provides guidance and tables for minimum pipe sizes, the final sizing of the discharge components also to be verified through hydraulic calculations to ensure that the required pressure and flow are delivered at the pump's rated capacity without causing cavitation or excessive friction loss. This is detailed in section 428. Then we come to the performance of and health of a fire pump are critically depend on the conditions at its suction inlet. Section 4.16.3 outlines these requirements. The most fundamental rule is that the pressure at the suction flange must never fall below 0 psi or 0 bar when the pump is operating. A negative pressure can lead to cavitation, where vapor bubbles form and collapse violently inside the pump, causing damage to the impellers and seals and a drastic loss in performance. To ensure smooth laminar flow in the pump, the suction pipe within a distance of a 10 pipe diameters from the suction flange must be sized according to the specific requirements of table 428. This table provides minimum diameters based on pump capacity to prevent flow restrictions and turbulences at the pump's entrance. The section 429 covers the installation of backflow prevention devices on fire pump systems. A backflow preventer is a crucial device that stops water from the fire protection system from flowing backward and contaminating the public water supply. However, its installation on the suction side of a fire pump introduces significant pressure loss, which must be carefully accounted for the system design. The key concern is that this pressure loss does not cause the pressure at the pump suction flange to drop below the minimum requirement, especially when the pump is operating at its maximum capacity. The location and type of backflow preventer are therefore critical. NFPA20 has specific rules, which we will see later on, about how far upstream and backflow preventer with certain valves must be placed to minimize its impact on pump suction. Section 417 provides the requirements for the discharge piping of the fire pump. This is the piping that carries the high pressure water from the pump to the fire protection system. Key components on the discharge piping include a control valve, which must be an indicating type valve like an outside screw and yoke, gate valve, a check valve to prevent water from flowing backward through the pump, and a discharge pressure gauge. The piping must be sized to handle the pump's rated flow without excessive friction loss, which would reduce the available pressure for the fire suppression system. The layout is also important. Similar to suction piping, arrangements that can cause turbulent flow immediately at pump discharge flange are prohibited, as they can create uneven pressure to the pump casing and impeller, leading to vibration and reduced bearing life. So we have some chat questions now. We can start a discussion over this. So what is unbalanced and turbulent flow? Unbalanced flow occurs when water does not enter the pump impeller evenly from all sides. This can happen if there is a fitting like an elbow or a T placed too close to the suction flange. The water is forced to one side of the pipe, creating a high pressure zone on one side of the impeller and a low pressure zone on the other. This imbalance puts lateral stress on the pump shaft and bearings. The concern is premature mechanical failure. NFPA20 tries to prevent it by mandating specific minimum straight pipe lengths, often 10 pipe diameters, we can remember from this previous explanation, between the pump flange and any fitting, allowing the flow to stabilize and become uniform before entering the pump. Next we have some slides of right and wrong installation, clear visual examples of correct and incorrect piping practices to prevent unbalanced flow. So on the right side, the diagram shows a sufficient straight run of pipe, at least 10 pipe diameters in length, between the pump's suction flange and the first elbow or T. This long straight section allows the water which becomes turbulent as it turns the corner in the elbow to settle back into a smooth laminar flow pattern before it enters the pump. This ensures even pressure distribution across the impeller. The wrong diagram shows an elbow installed directly at the pump flange. This forces highly turbulent and uneven flow directly into the pump, which can cause the damaging unbalanced forces we discussed, leading to vibration, noise, and reduced bearing and mechanical seal life. The third visual reinforcement of the critical 10 pipe diameter rule for suction piping is again clearly labels the required distance between the pump suction flange and the T or elbow as being greater than 10 pipe diameters. This consistent messaging underscores the importance of the rule. The wrong diagram is equally clear, showing the fitting placed too close. By providing multiple diagrams from different angles and contexts, our standard emphasizes that this is a non-negotiable best practice for all fire pump suction piping installation. We have multiple examples and diagrams showing these right and wrong installation examples. Ignoring this rule to save space or simplify piping is this is a direct compromise of the pump's mechanical integrity and its long-term reliability, which is unacceptable for a life safety system, of course. When a fire pump takes its water from water supply from a suction tank, a specific hazard must be prevented: vortexing. A vortex is a whirlpool that forms as water is drawn from the tank. If a strong vortex reaches from the surface down to the suction pipe inlet, it can draw air into the pump. This air entrainment leads to cavitation and a complete loss of prime, meaning the pump will not be able to move water. To prevent this, NFPA20 requires an anti-vortex plate. As the diagram shows, this is a flat vertical plate installed near the suction pipe inlet. The minimum size is 2 times the pipe diameter in both height and width. It must be placed at a specific distance from the tank bottom. We can say at least half the pipe diameter or 6 inches, whichever is greater, to ensure proper water flow while breaking up any forming vortices. The next slide combines two code sections, 4.16.5.4, 4.29.3.1, to give a complete rule on valve placement on the suction pipe. Section 4.16.5.4 is very clear, with one exception: no control valves other than a listed outside stroke and yoke valve, gate valve, are permitted within 50 feet of the pump suction flange. This is to prevent any valve that could potentially throttle the flow and create a disturbance from being placed too close to the pump. The exception is for backflow preventers. However, 4.29.3.1 states that if a backflow preventer that contains butterfly valves is used on the suction side, the entire device must be installed at least 50 feet from the pump suction flange. This ensures that the flow disturbance caused by the butterfly valves within the backflow preventer has dissipated before the water reaches the pump. Next, we are focusing on two primary types of valves discussed in NFPA20, the butterfly valve and the gate valve. specifically the outside screw and yoke type. Understanding the difference is crucial for correct application. A butterfly valve has a disc that rotates in the center of the pipe. When open, the disc is parallel to the flow. When closed, it is perpendicular. While they are compact, they can cause significant pressure loss and flow disturbance. An outside stroke and yoke gate valve uses a solid gate that is raised completely out of the waterway when opened, offering a straight-through flow with a minimum pressure loss. This is why NFPA20 typically mandates the use of OS and Y gate valve as the main control valves immediately on the pump suction and discharge, as their full unobstructed open position is ideal for fire pump service. Next, we have a repeated visual reference for the two valve types. We are reinforcing with this visual their distinct designs and design and applications. The butterfly valve is shown with its characteristic circular body and lever or gear operator, highlighting its space-saving design. The gate valve is depicted with its prominent threaded yoke, the external screw, which is a visual indicator of the valve's position. When the stem is protruding, the valve is open. This is the valve is open. This visual distinction is important for inspectors and operators. The repetition of this slide in our training emphasizes that you must be able to identify these valves in the field and understand that their use is not interchangeable. The choice between them is dictated by NFPA20 based on their location and function within the fire pump system to ensure hydraulic efficiency and reliability. Okay, the final requirement that we will explain today for a properly installed fire pump system is a valve supervision, which is covered in section 418. A fire pump is useless if a critical valve is accidentally closed, which is something we don't like, never. Therefore, all valves in the suction and discharge piping that are necessary for the operation of the pump must be supervised in their normal open position. The standard provides several acceptable methods for this supervision. The most robust is the connection to a central station. Proprietary or remote station alarm system that will signal if a valve is closed. Alternatively, a local audible alarm can be used if the area is constantly attended. For less critical locations, physical methods like locks or seals are permitted, but seals require a documented weekly inspection to verify the valve remains open. This ensures that any change in the status of a critical valve is detected and corrected promptly. Thanks for your interest to our training. Goodbye.